Today we're jumping into hodographs, and I mean really getting into them. You may have watched other YouTube videos about hodographs, but they may have left you more confused than helped. It's like Neo explaining the Matrix. You really want to understand, but you're just left staring blankly, and you sort of regret even trying. But believe it or not, hodographs aren't that hard to learn as long as you break them down step by step. So today we're starting part one of a two-part series on hodographs. We'll break down each part, build one from scratch, and show how to picture them in 3D. Plus, we'll explain how to find storm motion and share a hodograph cheat code you won't want to miss. I'm meteorologist and storm chaser Gabe Garfield. I've chased for over 25 years and have seen over 200 tornadoes, including 7 EF4s and 2 EF5s. I help new and struggling chasers find tornadoes safely. Let's dive right in. For this breakdown, this is where we're going. This part, we're going to introduce hodographs to begin, and then we'll break down their components. And then once we've done that, we'll build our own hodograph. Then we'll talk about the cheat code, and then we'll find storm motion on hodographs. And for the next part, we're going to find shear parameters from a hodograph. We'll look at the impact of storm motion on wind shear, and we'll understand the physical meaning of streamwise vorticity. I've worked with a lot of people on hodographs, including people in my storm chasing community for my course, and many of them struggle with hodographs. And it's not hard to understand why. The first part is that you really do need to understand the prerequisites before learning. And those are basically how wind barbs work and how to use polar coordinates to plot wind vectors. And the second thing is, it's kind of hard to visualize physically. It can be difficult to understand how to take information from a 2D chart and interpret that in a three-dimensional way. So hopefully in this video, you'll begin to understand how all of that works so you can have a better time putting together a tornado forecast. So before we go too much further, we need to define what a hodograph actually is. It's a chart that helps us to look at how the wind changes as height increases. And it can be used to quantify several meteorological parameters, including bulk shear, storm motion, storm relative wind, streamwise vorticity, and storm relative velocity. So as you can see, it's a number of parameters. It's pretty powerful actually, and can tell you quite a bit about how the atmosphere looks right now and how it might evolve. And you have an example at right that was taken during the May 3rd, 99 outbreak, the violent tornado outbreak in the Southern Plains, including the Bridge Creek Moore F5. And that is actually a pretty classic looking hodograph, and we'll dig into the shape of that in a few minutes. So to break down hodographs, we first need to stop at wind barbs. So let's do a little review. Wind barbs show two things: wind speed and wind direction. So we'll start with the wind speed. In this example case, you can tell the wind speed by the number of barbs that we have. These barbs are these like lines right here. You've got two of them, 1, 2, and each of them is worth 10 knots, which a knot is about 1.15 miles per hour. So that's roughly about 22 miles per hour is this wind, but in knots, it's 20 knots, okay? If you get a half one, that's worth 5. Now, if you get a full flag that looks like basically like a triangle, that's 50 knots. But in this case, you just have two of them, 1, 2, which each of them, again, is 10 knots. That's 20 knots. So that is the wind speed. Now, the direction, you see the cardinal directions here. You have north, east, south, and west. And this wind is in the lower right quadrant or the southeast quadrant, right? And that means the wind is coming from the southeast and it's blowing toward the northwest. But we call it a southeast wind because that is where the wind is coming from. So in summary, we have a southeast wind at 20 knots. Now we're ready to talk about wind vectors. And wind vectors show essentially the same information as wind barbs. They show wind speed and direction. So let's show that same southeast wind at 20 knots, except in terms of a wind vector. So what you'll notice immediately here is that rather than pointing towards the center of the circle, this wind vector or this arrow points from the center away from the center to the upper left quadrant here. So it points to the northwest or in the direction that the wind is going, right? So different than what we saw with the barb. And the second difference is that the intensity of the wind or the magnitude of the wind is indicated not by barbs or flags, but by the number of circles. So in this case, the wind speed is indicated by how far away from the center you are. So in this case, you've got 10 knots and then you have 20 knots. So wherever the tip of the vector ends up, that's the intensity or magnitude of your wind. And so that's how we represent a southeast wind at 20 knots in terms of a wind vector. By the way, if you're interested in leveling up your tornado forecasting, check out my tornado forecasting cheat sheet. It tells you what kind of numbers to look for and where to look for them. The link is in the description and in the comments. So to make this fun, I'm going to give you a little quiz. What is the wind speed and direction at this station? Is it A, south at 7 knots, B, south at 15 knots, C, north at 7 knots, or D, north at 15 knots? I'm going to give you a few seconds. If you answered D, north at 15 knots, you are exactly correct. So it turns out that this wind barb is coming from the north, right? So that is the direction of the wind. It's coming from the north and it has a long barb and a short barb. So the long barb is worth 10 knots. The short barb is worth 5. So that comes to a total of 15 knots. So you have a north wind at 15 knots. Here's another one. Match the wind barb at right with the wind vector. Is it A or is it B? So if you answered B, you got this exactly correct. This is a west-northwest wind at 10 knots. So you can take the station plot, which is west-northwesterly wind at 10 knots. We can tell this because it's coming from the west-northwest towards the station, which is east-southeast, at 10 knots, which is just one barb. Now, when we want to represent that in terms of polar coordinates, we, instead of going in the direction of the station, we go away from the station. So we start at the station and go away from it. In this case, we go to the east-southeast and we represent the magnitude or the wind speed with these rings. So it goes out 10 knots, which is this 10 knot ring right here. So that's how we determine that this is a 10 knot wind vector. So another question for you. What is the wind speed and direction at this station at the right? Is it west-southwest at 56 knots, west-southwest at 65 knots, east-northeast at 56 knots, or east-northeast at 65 knots? And I'll give you a second to think about this. If you answered B, west-southwest at 65 knots, you got this exactly correct. So in this case, the station plot shows a wind that is pointing toward the east-northeast. It's coming from the west-southwest. So the direction it is coming from is the name of the wind, a west-southwest wind. And we know it's 65 knots because we have a flag here, which is worth 50. We have a barb that's worth 10, and we have a half barb that's worth 5. So 50 plus 10 plus 5 is 65 knots. And the final quiz question is match the wind barb at right with the wind vector. Is it A or is it B? I'll give you a second to find this one. If you answered A, you got this exactly correct. So in this case, you see a wind coming from the east-southeast. But remember, when we plot hodographs, we plot them from the center toward where the wind is going. In this case, it's going toward the west-northwest. And we represent the length of the vector or the length of the arrow based upon how strong the wind is. And we know the wind here is 1 barb plus half a barb, which is 10, and 5, which is 15 knots. So we want to take this particular wind vector out 15 knot ring. So we have a 10 knot ring here, and 15 knots is about halfway in between 10 and 20. So this is where it'll show up. So that is why the answer is A. Okay, we're ready to construct a hodograph. You've got the polar coordinate system there. So let's introduce an example wind profile. And so you see it at right. And we call it a wind profile because it's a profile in height, meaning this is how the wind changes as you go above the ground. So for example, you have a surface wind right here. This is a station plot style surface wind. It's coming from the southeast and it's going to the northwest, but we would call it a southeast wind because that's where it's coming from. Now, the barbs are 1.5 barb, right? So 10 and 5, so that's 15 knots. And so that's our first wind. And then we go above the ground to 1 kilometer. That wind is coming from the south-southwest. And we have 4 barbs here. Each barb is worth 10 again. So 4 times 10 is 40. So it's a 40 knot wind from the south-southwest, and so on until we get to 6 kilometers. And this wind is coming from the west-northwest and is going to the southeast, but it is a west-northwest wind. And we have a flag, and then we have a barb, and then we have half a barb. So flag is worth 50, full barb is worth 10, half barb is worth 5. So that's a 65 knot wind. Okay. And now we're ready to plot the hodograph. Okay. So here's how you do it. First, you want to place the wind vector at the origin. So the tail of the arrow needs to be at the origin, and then we're going to mark the tip of the wind vector. So let's do the surface, for example. So in this case, the tail of the wind vector starts at the origin of the coordinate system, and we're pointing it in the direction the wind is going. In this case, it's going to the northwest, and we mark that point about 15 knots from the center. So you see the 10 knot ring here. It's about halfway in between the 10 knot and the 20 knot ring. Okay. And it's a surface wind. Now we need to repeat that for each level. We talked about the south-southwest 40 knot wind. So it's coming from the south-southwest to the north-northeast, but in the vector sense, we point it toward the north-northeast, and then we mark the tip. And we do the same thing until we get up to 6 kilometers, okay? And now we're ready to connect the vector tips. So from the surface to 1, and then from 1 to 3, and from 3 to 5, and from 5 to 6. Okay, so that those lines, the red line, the green line, the yellow line, those are essentially the hodograph itself. Okay. Here's one example of a hodograph from a SKU-T log P for a outbreak that happened in eastern Nebraska in 2014, the infamous Pilger double tornado outbreak. And what I'm going to try to do here is to match up the wind profile, which you can see here, kind of in the center. I want to match that up to the hodograph at right. So near the surface, you can see that you have this very light wind here that looks like about maybe even a quarter barb. It's a very tiny wind, and it's pointing to the west. Okay, so that's essentially what we're seeing here is that we see it pointing to the west. And then let's say at about 900 millibars, maybe 850, let's say. 850 millibars, you see this 35 knot wind. So that's pointing from the southwest to the northeast. And you can see here, that's probably just about here, I'd say, this half kilometer wind from the southwest to the northeast at roughly 35 knots. So maybe, actually it's a little bit further up here, maybe closer to that 1, okay? So that's how this is plotted, okay? And then we can go to, say, 500 millibars, and we can see we have a 45 knot wind from the west-southwest. And so if you're going to plot that on the hodograph, you'd go from here to, let's see, west-southwest at about 45. So you'd go out 10, 20, 30, 40, 45. So probably about here. Actually, I think it's probably about that 6 kilometer wind. So that's about where you'd plot it. So that's how this profile with sort of these station plot style wind barbs corresponds to the wind vectors that you see at the right. So another example I wanted to show you is from the super outbreak of tornadoes in 2011. And so I wanted to correspond the wind profile to the hodograph. And you can see that here with the surface wind. Surface wind, I don't know if you can see it too well, but we have 2 barbs and a half. So that's 25 knots. It's coming from the south and pointing to the north. And so when we go to the hodograph, we start at the origin and we move in the direction that the wind is going toward. In this case, it's going toward the north, right? And we go out the distance corresponding to the wind speed. So we know it's 25 knots. So it's 10 knots, it's 20 knots, and it's 25 knots. You see that? So that 25 knot out from the center to the due north, that corresponds to this guy right down here. Okay. We can do the same thing for 500 millibars. So 500 millibars, we have a flag and 2 barbs and a half barb. So that's 50, 20 plus 5. That's 75 knots from the west-southwest to the east-northeast. So when we go to the hodograph, we go to the east-northeast, right? And we go out a magnitude of 75 knots. So 10, 20, 30, 40, 50, 60, 70, 75. See how that works? So that, by the way, is a very powerful wind at 500 millibars. And here's another example of a hodograph corresponding to a wind profile. And this is actually taken, I would say, to the north of a warm front. And what you can see here, and what I really want to point out, is the surface wind is actually from a different direction. So it's coming from the northeast and going to the southwest at looks like about 15 knots. And when you look at the hodograph, you can actually see that happening here. So going to the southwest, about 15 knots. So you go 10 and then 12, maybe 15 knots. That's the surface wind. And that is the tip of the vector. And that's where you plot the hodograph and then you connect them all, right? And you can see how that creates different shapes. Now, this is a shape that you might see north of a warm front. And you start getting used to seeing these shapes when you get involved in meteorology. It's not just about plotting these things. It's about being able to recognize patterns by seeing the shape. So that's what we're going to get into, and we're heading toward that with this presentation. So now we're ready for the cheat code, the sickle-shaped hodograph. If a forecasted hodograph looks like a sickle, like you see at lower right, and the hodograph at left looks like that, and the other supercell ingredients are present, so that would include instability and moisture and lift, then big-time tornadoes are possible. Now, a hodograph like this, even in the presence of all the other supercell ingredients, doesn't guarantee big tornadoes. You still have to have a supercell, and sometimes you get a squall line and have too many storms. But generally speaking, if you see something like that in the forecast, it's generally a good sign for tornadoes. So we're back to our example hodograph, and we can take a closer look. Notice that the hodograph trace is the difference of winds between 2 heights. So, for example, the surface and 1 kilometer. So here's the surface wind. It's from the southeast, 15 knots, connects with the hodograph there. And then the 1 kilometer wind is from the south-southwest at about 40 knots, connects to the hodograph there. And the red arrow that connects those 2 vectors is the hodograph itself. So the hodograph itself is the difference of winds between 2 heights. And what is this difference called? Vertical wind shear. So basically the hodograph shows us in a 2-dimensional plot, basically the potential for spin in the atmosphere. But how does it look in 3 dimensions? Let's find out. By the way, if you're interested in leveling up your storm chasing game, check out my course, The Tornado Chaser Transformation. In it, I share my entire playbook, literally everything I know about tornadoes. In about 6 hours, it comes with an online community, comes with challenges and prizes and all sorts of good stuff. If you're interested, check out the description or the comments. Okay, let's plot a hodograph using our example wind profile. So in that profile, there was a southeast wind at the surface, and a south-southwest wind at 1 kilometers, a westerly wind at 5 kilometers, and a west-northwesterly wind at 6 kilometers, pretty fast. So to make the hodograph, you connect the tips of the wind vectors. So from surface to 1, we have this connection. From 1 kilometer to 5 kilometers, we have this connection. And from 5 to 6, we have this connection. And all of this together is the hodograph. And so let's drop the winds so we can see what that looks like. There's the hodograph in 3 dimensions. Okay, now we can talk about hodographs and the impact of vertical shear on the behavior of storms. And we'll use this case, which is April 14th, 2012 in Northwest Oklahoma during a tornado outbreak. And we'll focus on this storm near Radon. Now that storm, as it moves to the northeast, you'll see a left split come off of it, moving towards our net. So a storm kind of splits off of it to the north. Watch as we go forward. So you can see we almost have mirror image supercells southwest of our net there. And this is not an accident, and it is actually determined by the shape of the hodograph, which we will get into next. Okay, let's find the storm motion using the bunkers method, which will help us to determine the left moving and right moving supercell motion. So first, we're going to find the average wind, which is in the middle of all the winds. You can see that here. Basically, the winds are all around it. That's roughly the average of all those vectors. And then you're going to draw the 0.5 kilometer to 5.5 kilometer shear vector, which basically, if you go from surface to 1, it's about halfway in between to start that vector, and then halfway in between the 5 and the 6, which is about there, right? Halfway in between here and there, halfway in between 5 and 6. And then you're going to draw a line that's orthogonal to that line that passes through the average wind. And then finally, you'll plot motion 15 knots to the right and to the left of that. And basically, in this case, your right mover is going to be moving east-southeast at 25 knots, which is what you see here. And your left mover is going to be going, let's say, northeast at about, let's see, 10, 20, 30. Let's see, did I get that right? 10, 20, 30, 40, 45 knots. So it's moving pretty darn fast in this case. So that's how you would find the right moving and left moving supercell motion. All right, that's it for now. Thank you so much for watching. And if you got some value out of it, please consider liking and subscribing. And we'll see you for the next video, which is the conclusion of this series on hodographs. Thank you very much. Take care.